So last time we introduced this concept of how do we prove that a language is not regular, which turns out to be a significantly harder question than proving that a language is regular. So we came up with this format where we're going to start with an infinite regular language. It needs to be an infinite regular language because if it is finite, then of course it is regular. All finite languages are regular. So we're going to assume that this unknown regular language, so this unknown infinite language is regular. And we're going to proceed with a proof by contradiction. And that just looks like we are going to assume that it is regular. And we are going to show that it does not adhere to this very important property of all regular languages, that we can have any string in that language, and we can decompose that string into three components, x, y, z, that adhere to the following constraints. The length of xy needs to be less than or equal to m, the number of states in the DFA that represents that language. And the length of y, which is greater than or equal to 1, saying that the loop size for this has to be at least one node of looping back to itself, basically, would be the shortest possible loop. And we know that within the number of states in a DFA, we have to reach the end of that loop. By the time we have read that many characters into the string, we'll have gone through enough transitions to visit every state and then go back to some state that we have already visited. Because it's an infinite language, we can come up with a string that is arbitrarily long. So we should be able to break this down such that that string is going to be longer than the number of states in the DFA. If that is the case, then there must be some loop. So we will go prove that that loop can't exist, at least in a way that adheres to this particular constraint. All right, so we see that for each pumped string W, we say that there's going to be some segment in the middle that can be repeated. So for every string, you need to break it down into getting to the loop, and after the loop, which is this X, Y, and Z, getting to the loop, repeating the loop some number of times, 0 or more, and then getting to some final state from the exit of that loop. So we could then make an arbitrary set of all such W where this pumping happens an arbitrary number of times. So XZ is a string in the language, XYZ is a string in the language, XYYZ is a string in the language, etc. And every string that is in the language has to be able to be broken down as such. If it cannot be broken down as such, then we have a problem. And if you come up with that breaking down that adheres to these requirements and pump the string some number of times, you create a string that is not in the language. Then that also works as a counterexample to that proof, which is the direction that we're going to be going. Questions about just kind of the general idea of this? So we'll get lots of examples with it. But I want to the best of my ability, make sure this at least high level concept is clear before we start going into an example of it. So how do we feel? Does this concept make sense without really having seen it? You could show thumbs, understand it. Certainly need some examples to really see this happen, but part of it, no, need more explanation here before we dive in. So one way you can think of this is that you are, because I love games so much, playing the world's most boring game with an opponent. This is not a fun game, but I can phrase it like a game. Would never play this game in my own spare time. So it's a game played between two players, and these players are competing with one another. The goal of the first player is to show that the language is regular. And the goal of the second player is to prove that it's not. So, well, the goal for player one is to make it as difficult as possible on player two. If the language isn't regular, then we can prove that it's not regular. But player two can either have a very easy time with this or a very difficult time with this. And player one needs to make sure there are no possible counterexamples to their idea, but they're gonna lay out the baseline for player two's proof, saying, I think it's gonna be as hard as possible if I choose this. So player one is gonna pick a value for the number of states in the DFA. So this is the suppose a DFA with this many states exists. It represents this language. This M can be any value. But when you actually go to write the proof for this, you will need to stick with a variable here that shows no matter what player one picks for M, then the rest of this follows. But to get an idea of this, you could just start by picking an arbitrary value. If you pick an arbitrary value, it is not a proof, but it is, again, a good way to dive into the process. Player two then says, okay, player one, you gave me this value for M. My task is to find a string in the language such that that string is longer than this M. Can be the same length, but in general, you want to pick something that is longer, because then we have to have that looping process in the DFA. We can't just have visited most or all states without going back to a state that we visited before. All right, now that we have the string, back to player one. Player one's job is to find X, Y, and Z that adheres to, again, these two constraints that we saw on the previous slide. So the length of X, Y must be less than or equal to M, whatever M was picked here. And the length of Y has to be greater than or equal to 1. If you do this intelligently, the next step is as difficult as possible for player two, which is the goal in a competitive game. You could choose this in a way that makes it really easy, but that is boring. And it also doesn't prove anything. So finally, player two is going to pick the number of repetitions of the loop such that some pump string X, Y to the I, with the I that they pick, Z, is not in the language. If player two is successful, then player two wins. If player two cannot do this, then player one wins. Again, this is not a proof, but it gets you in the right mindset for how do I actually show this. So you go from playing this game to constructing a proof that says, regardless of the value picked for M, here is the mathematical layout of why we will always have some value I to pick in this step 4 that breaks this whole thing, and we can generate a string that's not in the language. That is the full proof. But it still follows these steps just in general rather than as a specific. So if it is possible for player 2 to win this game at all, if there exists an M such that all of this, then the language is not regular because it doesn't abide by this. But we will show what that looks like in more detail here in a moment. So just because player 1 wins the game does not mean the language is regular, is also a very important thing to note. Questions on phrasing this as a game? All right. Let's start by playing the game, and with 3 people in here, it's going to be a little bit challenging. I'm going to hop in as some player for somebody. But somebody take the role of player 1, somebody take the role of player 2. First of all, what is this language? We were to phrase this in English.
A palindrome?
Yeah, well, yeah. So some string followed by that string in reverse. which is a subset of all palindromes, because palindromes can have a middle character, like ABCBA, which would not appear to WWR, but it's the subset of palindromes that do have a portion followed by a portion in reverse. So first and foremost, what do we think intuitively? Well, we're saying that this is not regular, but does it make intuitive sense why this isn't regular? What are people's thoughts on that? Yeah, it can have an arbitrary length. We don't set bounds on how long this W is before we start reversing it. So a finite number of states in a DFA would allow us to say W is at least that length. But by the time we've iterated looking for the first character, the second character, the third character, the fourth character, the fifth character, the sixth character, etc., then we would need to have identified that it's time to go back in reverse so that we could go back and visit the states that we visited, kind of waiting to get back to the beginning. But as soon as we picked a string that was longer than that, we would say your finite length DFA doesn't handle palindromes where W, the length W, is longer than that number of states that you picked to be the finite number of states in your DFA. That's exactly right. So that's the intuition for why this isn't regular, and I think taking that intuition with you will help you with this proof.
Would it also help that you can't have a loop with this, like the palindrome doesn't have a loop. It can't, or it can't.
Well, it will. The idea is if we were to do this for something like all WWR such that W is in the star closure of this and the length of W is less than or equal to 2. We'll choose something that's pretty short, because now it's regular.
You do like ABA or something like that, but yeah.
Yeah, so that's not WWR. That would be a palindrome, but there's no. Like AB would be the W part and BA would be the other part. So if we were to draw a DFA for this, you want to start in a final state, because remember the length of W could be 0. And now if we see an A, then we would go to Q1, and if we see an A from here, we would go back. And then if we see, from an A here, no, it has to be like less than or equal to 2. So AA would be fine, BB would be fine, but anything other than that would fail. So we'd have another BB from some other state, Q2. If we wanted to make it length, I guess no, we said length W is less or equal to 2. So now we have to be able to handle that there's AA. So there's another one state here on A, oh it's Q3, another state here on B, oh it's Q4.
Increase the length of that from 2 to like 5.
The issue is now that you can loop this and generate arbitrary things that are longer than that. So I guess you would not want to go back, because you want A, B, B, but now you don't want to have this branching from this state. It is possible to do, but my plan for this has already been foiled by myself. But as soon as you place that arbitrary restriction, you just have to say, the counter example is for some W that's longer than that, than the number of states that you end up having, given that you placed a restriction on the length of the size.
So you're not really looking for a loop and showing there is one. You're just rather
Saying basically, if there is a loop, then I can generate a string that's not in the language, and there has to be a loop in order to generate strings that are longer than the number of states in the DFA. So the generic proof is regardless of the number of states in the DFA, there exists a string in the language that is longer than that can be broken down into XYZ as such that we can pump with a string that's no longer in that language.
Because the only way to get a string that's longer than the number of states is if you can somehow loop somewhere, you need to find that loop and show that it
Yes.
exists, okay.
So let's go ahead and break into player one and player two and see if we can play the game here with WWR as an example. And excellent, now I have a fourth person, so I can. All right, so we're playing the pumping lemma game. I've turned this into the world's most boring game. So I think we have a pair here and a pair here. This does not matter, but who wants to play the role of player one in your two groups? All right. So player one here, doesn't matter. Player one, excellent. So player two and a player two. Player two gets the harder role. All right, so you're going to pick a value for the number of states in the DFA. This is a strange claim that says a DFA with exactly this many states exists that solves this problem. Which we already know we can't construct a proof based off of that. We have to say no DFA of any finite size exists. But again, this proof is just this game is just to help you with that proof process. Starting with an example. So pick a value for M. Player two will say, all right, given that number of states, I'm going to intelligently, this is a tough problem, you have to choose the right string. Pick a string in the language of length greater than or equal to M. Not just any string. A string that is going to pigeonhole player one into breaking this down in such a way that this is possible. So player two needs to be thinking ahead in this game to this step. Picking a string that says, no matter what player one does, I will be successful here. There will be intelligent and not so intelligent picks for the string that will either make this possible or not make this possible. So again, that language is some string W followed by that exact same string in reverse. So player one, pick some number of states that you think would be a great solution for a DFA for this language if it existed. Choose something that is reasonably short so that player two doesn't have to generate the world's longest string.
So you just write.
Take something less than 10.
You just write a string that's like in that. Right?
So player one is picking just this number M, a number of states in the DFA. So maybe you say 5. I think that this language can be represented in a DFA of 5 states.
Player two needs to show that.
Player two is going to pick a string such that I don't want that yet. Player two is going to pick the string such that I want this. There needs to be length greater than or equal to M in that string, but we have full power player two over exactly what that string looks like. So let's say the alphabet we're using here is AB. We can only have A's and B's. But you get to pick the string. So if player one says M is 5, pick a string that adheres to the language. So it has to be in the language. And thinking ahead, knowing that player one is going to get to choose this decomposition, what can be pumped from there. So there is a form of this such that player one is pigeonholed and player two will win the game. This is the really important step. If this language isn't regular, it doesn't matter what player one picks here. Player two can pick something such that player one has no choice but to let them win the game. Really hard to get that intuition. But the question that I will have for you, and I'll give you this to help you out. We should pick a string such that the first M characters are all A's, and W is of the form A to the M, B to the M. Does that make sense? So player one picks, let's choose something slightly smaller just for reference. Player one picks 3. I think a DFA of 3 states exists. So now, what is a string since the first M characters are all A's? W is of the form A to the M, B to the M, and the string picked is of the form WWR. We need all 3 of those constraints to be true. So we could choose A, B, B, A. So here is an excellent string idea for player 2. So the first M characters are all A's. W, the first half of this string, is of the form A to the M, B to the M. And the entire string is a palindrome of that form, where we have W, WR. A string exactly like this pigeonholes player 1 according to the rules of step 3, which says that now we need to break this string down into X, Y, Z. Such that X is getting us to the loop, Y is at least getting us through the first loop. And then Z is getting us to the final state from that. But we know, because there are only 3 states in this DFA, that we have to get to that loop within the first 3 characters. So XY has to come from this segment of this string. This gets us to the loop and iterates the loop. So how do we even get to these beats? It can't happen. So now player 1 is forced to pick an X and a Y that are all A's, because player 1 has total control over what of these A's is X and what of these A's is Y. Remember that Y has to be at least 1 character, so really you only have 3 choices. Either we have X0 is the empty string and Y0 is AAA. Either that or X is A, Y is AA, or X is AA and Y is A. We can't have X being AAA and Y being the empty string because the length of Y has to be at least 1. That's one of those constraints. You have to appear in the first M characters. So player 1, you have to pick one of these 3 things. And player 2 says, aha, but regardless of what you pick, this is the loop. So if I pump whatever you pick here as the Y, some number of times, we're gonna create a new string. For the sake of fun, let's say that player one picks this and says, all right, we're gonna run with this. This particular breakdown of getting to the loop and iterating the loop looks like this in our DFA. Player two says, great, I'm going to pump this twice. Which gives us the string A, B, 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 A. So if this string was possible to construct within that DFA, this string would also be possible according to this breakdown. Right? If this is getting us to the loop, this is iterating this loop. If we do this loop twice, we would end up with this string, keeping everything else constant. If this is possible to produce, then this is possible to produce. If this is possible to produce, then this DFA can't represent this language because this string is not in that language. It does not adhere to these rules. So this DFA can't exist. Now we've shown that no DFA with exactly 3 states can exist. Great. What does that say about DFAs with 4 states? Nothing. So we need to construct this proof in the abstract so that this works regardless of this number chosen. So we're going to have to use math notation that says, now instead of picking 3, we're going to pick. We need to variabilize it. We need to say that there exists some finite DFA of size m. We'll proceed now by taking this and saying that if you construct something of the form a to the m, b to the m, b to the m, a to the m. That is a string that would be legal in that language. That is something that we could say, this adheres to that structure. So this DFA of m states needs to be able to produce this, regardless of what m is. So now we see that player one is pigeonholed into breaking down an x and a y that is nothing but a's. That will always be true. So this has to be the x and the y. The logic from here is that the loop is all a's. We have constructed an example string such that getting to the loop and iterating the loop has to happen with all a's. Great. Now you just show that by pumping y, whatever y happens to be, you know its length is at least 1. So that's going to be adding at least 1 a to this segment without modifying anything from the rest of the string. Doing that, regardless of the size of m, breaks this language rule. So you've gone from something that is specific into something that is kind of vague and generic, but works regardless of whatever you instantiate m with. So that is how we're actually going to be doing this. But again, I think the game helps people to start to visualize and draw out what happens if I choose something of length 3, what happens if I choose something of length 4, but you're not done there, you have to finalize and put that variable back in its place to show that no DFA of any size, any finite size can exist to represent this language. How are we doing with that? That's kind of a leap from the game, but that's the process we want to go down to prove this. Yeah.
So could a general way of doing this be like, find it for like some arbitrary n, like try it with 7 and then try and find that pattern to generalize it, or does that just work this way?
Absolutely. With a lot of practice, you can start here, but I find that it makes a lot more sense intuitively to people who are just learning this to start out by picking an actual value and going through the game and seeing what choices player 1 and player 2 have. And that can help you to figure out what does the structure of that string that player two needs to pick, what does that look like? And then if you find something that works, the real test is then replacing that constant with a variable and say, does that work in the abstract? Does that work in general? If you can show that it works in general, then you're done. But as true with most math proofs, it's not just the application of rules. There's problem solving, there's critical thinking in there to figure out how can I draw these conclusions. So starting with something that is intuitive to you will be very important to helping you to be able to make those leaps, draw those logical connections. This is what has worked for me. If this is confusing, we will have plenty more examples of it, as well as we may finally see our first person in office hours in this class, which would be great. I am highly underutilized right now. I have nothing to do. Please come give me something to do. I am bored. I am crying in my office, waiting to feel needed by my students. And not actually quite that bad, but I would love to see. Questions on this process before we get additional examples with it? Maybe here's another visual that will help. So this is kind of what I tried to draw out on the board. This is kind of the slide version of it. So we have a generic form that adheres to this, A to the M, B to the M, B to the M, A to the M. We know that X, Y has to happen within the first M characters. So we break down into no matter what X and Y are chosen here, we make a generic argument that Y has to be all A's and at least one A. Because of this, when we pump that, which means that we expand or contract Y, we duplicate Y some number of times, or we remove Y completely. Because this needs to work regardless of the value of Y. So Y could be 0, and we end up taking characters out of the string. Then we expand this portion, and it no longer adheres to this, which no longer adheres to that. Questions? Show of thumbs, how much sense does this make? It's better for you to be truthful with me here, just to know how, where people are. I saw this half the room, how's this half the room doing?
I just need another example.
Yeah. Well, you'll be surprised by the title of the next slide. All right. Alphabet A, B, a language is all strings with more B's than A's. Is this language regular? The answer is no, it is not. But how could we prove it? We'll need to use the pumping lemma. So you can think of it in terms of the game. Feel free to break into pairs again and start to play the game. Put your brains together. Find that string type that makes it really easy to show. You pump some section in the first part, you end up with strings not in the language. as such, but I'm imagining like a new Saw movie where Jake says, do you wanna play a game? And then it's just like, let's prove the pumping lemma, and everyone's like, no, just kill me. Put me in a horror film, just do anything but make me prove the pumping lemma or show the pumping lemma. And Jake's like, no, let's prove this is not regular with the pumping lemma. Any ideas about this next part? So. We choose some M. You can either think of that as an actual value like 3 or 4, if that helps you to start thinking about this. Or you can just move forward with the variable, assuming that there are M states in the DFA. How could you construct an intelligent W that's going to make this proof as easy as possible? There are better choices and there are worse choices here, and it's really important that you choose something that will make this proof kind of slide into place. Any thoughts on what the construction of this string might be?
Again, BGB on this one.
That is a phenomenal choice. In fact, I would argue that that is probably the optimal choice. What led you to say that?
For similar reasons, so as example, if n is a number, then x, y has to be all A's. Meaning, if you pump it just once and b is only n plus one number, then the numbers of A's and B's will be unequal, which is not interlinked.
Right, we know that the length of that loop has to be at least 1, so iterating that loop one more time will at least tie the number of A's and B's. If not, add even more A's than B's into this string. And it doesn't matter what player 1 did with the XY breakdown, we know that there is at least one more A in the pump string if we take I to be 2, the number of times we iterate the loop. Because this base is XYZ, so XYYZ will include at least one more A, which will break the language. Right, we'll create a string that's not in the language. Does this make sense as a? The structure of these proofs break down to exactly that kind of intuition. How can we construct a good string type such that the rest of the proof will just slide into place? The logic is just there. You think about it, you go, yeah, of course. If I add more A's to the string, it won't adhere to the language. And because of the restrictions, XY has to come in the first M characters. It's just simple logic from there. Again, that hard part is coming up with A to the M, B to the M plus 1 as a structure to work with. So we know from this that Y has to be all A's. We pump Y, the resulting string cannot be in the language. Does that make sense? People hopefully coming up with something, or at least seeing it here makes it make more sense as to why that's a good string to choose. Does it make sense now, not so much going for the finite number of states, like 3 or 4, but actually carrying M through the whole proof? Questions on this example? Yeah,
I guess it's in this example, but. Are you going to give us another example, or so can we get one of a regular language where this would be not possible?
we can certainly go for that. I do have another example, but I don't know if it adheres to that. It does not adhere to those constraints. But yeah, it would be good to show, take a regular language. That means a DFA does exist. That means that there is no possible way that you can construct this in a way that does not work. Yeah, I'll see what I can do with that. All right, we're gonna go AB to the N. A to the K. Such that N is greater than K. And K is greater than or equal to 0. So this is a little bit more complex. N repetitions of the substring AB. Followed by some number of A's, bounded by 0. And K minus 1. Sorry, N minus 1. So now it's a little bit harder to think of what that string looks like. Any intuition for why this is not regular? This has some slightly different intuition from the last couple, so that's why I want to ask that question. First half of the question is, if we just took the left part of this, AB to the N, is that regular? Yes, it is regular. We just construct a DFA that goes from a final state to a non-final state on an A. And then back to it on a B, A, B, doesn't matter how many of those you have, and if you see a B from that first state, you go to a trap state. If you see an A from here, you go to a trap state. That's the entire DFA. So what makes this non-regular is that we have this right-hand side A to the K. And we know we need to have stored somehow, we need storage for the number of times we iterated that AB. But DFAs can't easily store numbers like that, or if it does, it tends to multiply the size of the DFA up to some cap. But because N is unbounded, K is also unbounded in general. So we can't put an upper bound on the maximum number of times we would have done that. So we need to know how many times we iterated to it, to know the maximum number of A's that we could read before we went off into a trap state that says we've seen too many A's at the end of this string. So it again boils kind of down into storage. We need to know how many times, we need to know what N is by the time we're done reading ABs and transition to reading A's. So what does that tell us about a good choice for a string?
With I think 2 be a good choice.
For. Yeah, we need a string W that's in the, language, that's at least M long, where M is the size of the number of DFAs. That's the number of states in the DFA. But if M is some arbitrary constant, then we need some string based on M such that we can ensure that this string is longer than the number of DFAs which states in the DFA.
When we're gonna do this. ABA, or just.
What if M is 10,000? Then that string is no longer longer than M.
Oh, sorry, I remember like the smallest you could do is that,
Yeah,
and then from there, it's just adding more and more.
yeah, you're right. AB would be the shortest possible string in the language. N has to be greater than K, so N's at least 1.
I'm not an exact answer, but I'm thinking if the right side is what breaks it from being regular, the right side has to be somehow included into our counterexample, right?
Sure.
So I have like small examples that work, but I can't generalize it.
Yeah. So we are out of time. What I'm gonna give you kind of as an exercise between today and tomorrow, and of course, in addition to your homework that's due on Wednesday, is here's a good breakdown. So rather than getting stuck on trying to figure out what that breakdown should be, what that string should be, here's a good choice for the string. See if you can work through taking this string and saying, no matter what we choose to be X, Y, and Z, we can construct something in such a way that we can prove that this language is not regular. And we'll come back tomorrow morning. And we will actually write out and show the logic behind this. All right, I have office hours starting now in my office. If anyone has any questions about anything we covered today, anything on the homework that's due on Wednesday. Yeah, and we're taking an exam.